Okay, one of the things we're going to work on today is the squeeze rule for evaluating limits. But we've got examples 5, 6, and 7 to show you. 3 more limit type problems that you'll see on the AP exam, and hopefully ways and strategies to recognize what type you're getting. So this is L'Hopital's rule. This is the limit as x goes to 2 of natural log x plus 3 minus natural log 5 all over x minus 2. Well, the first thing I notice is when I plug a 2 in directly, I like to see what's going on. So on the bottom, I see I'm going to get a 2 minus 2, 0. But more important, if you're going to use L'Hopital's rule, you can't just have a 0 on the bottom. That doesn't cut it. You got to have an indeterminate form of 0 over 0. Or if you have an infinity on the bottom, you've got to have an infinity over infinity. Or there's some other peculiar ones. 0 over 0, infinity over infinity, negative infinity over negative infinity are the most common ones you'll see on the AP exam. But anyway, as we progress here and plug a 2 in wherever we see an x, I hope it's plainly obvious to you that we're getting natural log 5 minus natural log 5 on top, which gives us 0. A 2 minus 2 on the bottom, which gives us 0. We get 0 over 0, which is an indeterminate form. And this has bells going off in my head immediately. When I get an indeterminate form, I'm thinking L'Hopital's rule. So when I get L'Hopital's rule, what I do to execute L'Hopital's rule, I simply take the derivative of the top and the derivative of the bottom. Isolate the top, take its derivative. Isolate the bottom, take its derivative. You are not to be using the quotient rule here. That's just going to screw your endeavor up. So I do that. I take the derivative of the top, and I get 1 over x plus 3. Remember, natural log 5 is nothing more than a constant. I take its derivative, and we'll get 0. I take the derivative of the bottom, the derivative of x minus 2. I just get 1. Now attempt to plug in that limiting value one more time. Plug in a 2 for x. What do you get? Well, it's pretty clear to me that I'm going to get a limiting value of 1/5. And if you took a moment and used your calculator, you could verify this and put in your y equals screen natural log x plus 3 minus natural log 5 all over x minus 2. Be parentheses careful there. And you'll see as you get real close to the number, the x value of 2, right on 2, you're going to get an error. But a 1.9, 1.99, 1.999, you're going to see the decimal getting very close to 0.2 or the fraction 1/5. The other thing I'll caution you about with L'Hopital's rule, you might get an indeterminate form, attempt L'Hopital's rule, and not get an answer. You'll get an indeterminate form again. Try L'Hopital's again. Derivative of the top, derivative of the bottom. Insert the same limiting value again. This might even require 3 attempts before you finally get something that makes clear sense. So don't be afraid to try and try again. I really haven't seen an AP exam go over 3 attempts at L'Hopital's rule. So, you know, there's a limit to how many times they'd have you do that. But know that oftentimes with L'Hopital's rule, once, twice, 3 times, you'd have to take the limit of the top and the bottom in order to finally arrive at a finite limiting value. All right, let's look at number 6. This one's kind of cool. A lot of students get hung up on a problem like this, and it's not terribly difficult if you just said 2 words to them as a hint, if that was permissible on the exam. If you could just tell them, hey, graph it, then they might be able to do this. So, you know, at first I'm in panic mode a little bit. The limit as x approaches 3 from the left. That from the left thing bothers me. Absolute value of x minus 3. The absolute value bothers me over x minus 3. I'm not sure how to do this. Well, you know, taking derivatives of this thing is really not a potential for us. We haven't been dealing in derivatives of absolute value at all. There's no factoring of things that can cancel, etc. L'Hopital's rules is of no use. So let's try to go ahead and graph this thing and see if we notice a pattern. You know, as complicated and a little bit scary as this problem looks, absolute x minus 3 over x minus 3 shouldn't be too terribly difficult. So there is a part of me that says this ought to be easy. So Why did I choose x values 0 to 6 instead of like negative 3 to 3? It's the 3 that is the important input here. I know 3 minus 3 on the bottom gives me 0, so I've surrounded 3 with numbers, all right? And so I'm going to put in 0, 1, and 2 for x and get negative 1s. 4, 5, and 6 I can get positive 1s. So just to give you an idea, if I put a 0 in for x, I go 0 minus 3 and get negative 3. I take the absolute value of negative 3 and I get 3. So when I put 0 in, I have a positive 3 on top. On the bottom, I put a 0 in, and I go 0 minus 3. I get negative 3 on the bottom. 3 over negative 3 gives me that negative 1. The same type of pattern exists there for values 1 and 2. For values 4, 5, and 6, nothing tricky is happening here. If I put a 4 in for x, I get a positive 1 on top. I get a positive 1 on the bottom, which yields a positive 1 output. All right, so I'm going to go ahead and graph this to give us a better idea. I know the outputs are either negative 1 or positive 1. I've got inputs 0 to 6. My graph's going to look like this. I have negative 1 outputs for values 0, 1, and 2, and I have positive 1 outputs for values 4, 5, and 6. Now, what's going on here as I approach 3 from the left? As I am approaching that number 3 from the left-hand side, I can see that I remain down at negative 1. And so, to evaluate this limit, all I need to do is graph it and approach 3 from the left and realize that I'm on the negative 1 road. This limiting value is indeed negative 1. Lastly, number 7. This is that squeeze theorem. This is kind of new kid on the block for Calc AB students. And I can kind of give you a clue here to let you know, because it will not say, hey Chachi, use a squeeze theorem to evaluate this limit. It won't tell you that. So something's got to catch your eye. And what catches my eye here, and I have bells going off in my head when I see it, is that sine 1 over x. Now, I'm going to show you something that's going to look very complicated, but something in common with these graphs. Check this out. I know it, trafficy mess. But I've got 3 functions on the left. The sine of 1 over x, the cosine of 2x, and the sine of x minus 3. The point of emphasis here is when you take the sine or cosine of any quantity, you could get some funky things happening horizontally to the graph, but vertically, each of these graphs, each of these functions exist no lower than negative 1, no higher than positive 1. They're all squeezed in between a range of negative 1 and positive 1. You'll see how that comes into play here as we do this problem. But the sine of 1 over x catches my eye as a potential squeeze theorem here. So this is just in words important to notice that these functions, the sine of whatever, the cosine of whatever, they range between negative 1 and 1. Let's see how that is important as we evaluate this limit. So, again, this is the same exact problem we already looked at. The limit is x equals 0 of 4 plus 3x squared sine of 1 over x. And I'm going to give you some steps here. So, what I'm going to do is begin with a real simple sine of 1 over x. And I'm going to squeeze it in between negative 1 and 1, like this. The sine of 1 over x is greater than or equal to negative 1, is less than or equal to positive 1. Now I'm going to use algebra steps and build upon that function. And I'm going to apply these algebra steps to all 3 parts, the left, the middle, and the right. Take a look. The next step is to multiply all 3 parts by 3x squared. Maybe you can see in your mind's eye what this new compound inequality is going to look like. If I multiply all 3 parts by 3x squared, I'm going to get a negative 3x squared on the left, a 3x squared sine of 1 over x in the middle, and a positive 3x squared on the right. I still have that sandwiched inequality. Now I'm going to perform another algebra step. I bet you know what it is. I'm building upon that function. The next thing I'm going to do to all 3 parts, I'm going to add plus 4. to all three parts. I'm going to add 4 on the left. I'm going to add 4 in the middle. I'm going to add 4 on the right. Now, it doesn't look like we've accomplished anything except making a complicated problem more complicated. But the beauty here of the squeeze rule is this. I know that function in the middle lives in between the guy on the left and the guy on the right. Greater than or equal to the guy on the left, less than or equal to the guy on the right. And I'm going to be able to successfully evaluate the limit of the far left expression and the far right expression. Take a look. I'm going to evaluate the limits of the front and the back, or the far left and the far right. So, far left, the limit as x goes to 0 of 4 minus 3x squared. I plug a 0 in for x. Ding! I get 4. I now evaluate the limit on the far right as x goes to 0 of 4 plus 3x squared. I directly plug a 0 in for that x. Ding! I get 4. Mind you now, I couldn't have just plugged a 0 in for x at the beginning because I have a 0 in the denominator of that sine function. Okay? So what's nice here is that we have made two expressions, built two expressions that we can indeed evaluate when x goes to 0. So the punchline here is that therefore, if the expression on the left is 4, the limit of the expression on the right is 4. The guy sandwiched in between them, I'm talking about the limit as x goes to 0 of 4 plus 3x squared of sine over x, of sine of 1 over x equals, it's got to equal 4. It's got to equal 4. So as long as we were able to begin with that sine function yielding between -1 and 1, ranging between -1 and 1, just build upon that thing, and you'll find, keep your fingers crossed that you get an identical number far left and far right, and you can apply that limiting value to the middle expression that is sandwiched or squeezed in between the far left and the far right. That's how the squeeze theorem works. So you guys, there's 7 examples of typical limit problems you may see on the AP exam, and so now maybe you run into some limit problems cold turkey, and at least you have it kind of narrowed down to some strategies that you might utilize to solve for those. So hope that's helpful. This is AP Calculus AB, evaluating limits and figuring out when specific limit strategies should happen. I wish you well. Over and out.